So in this second lesson, I wanted to focus on some of the kind of more complicated questions. We're actually going to have a look at two of the harder questions from exercise 6C that you set before. So don't worry if you found some of those a little bit tricky. So a basketball player is standing on the floor 10 meters from the basket. The height of the basket is 3.05 meters, and he shoots the ball from a height of 2 meters at an angle of 40 degrees. So I'm just going to draw a very basic picture. Okay, so here's the hoop, and here is the basketball player. And it says the height of the basket is 3.05 meters, and the height of the person that they shoot the ball from is 2 meters. And it says given that the ball passes through the basket, okay, so we are shooting at an angle of 40 degrees, it says, and it follows this trajectory and goes in the basket. Now, the important things to understand here is this point here, where it goes through the hoop, we could write this as like a coordinate. So it's x coordinate, because it says that he stands 10 meters away from the basket, would be 10 meters. And then the y coordinate would be 3.05. Okay, that's its coordinate if we use this point here as the origin. If instead we did it as this point here as the origin, so where it's starting from, rather than 3.05, we could actually use it as 1.05, because it's 1.05 meters above where it started. So I'm going to do it relative to this point here. I think that makes it a bit simpler. So now let's just look horizontally and vertically. We don't know what the speed it was that it was thrown at, so we're just going to use u. So that means the vertical part would be u sine 40, and the horizontal component would be u cos 40. Let's deal with vertical first of all. So vertically, we want to get to a displacement of 1.05 above where it started. U is u sine 40. A is minus 9.8. And t, we don't know what t is. We can just do it in terms of t. So we could now use s equals ut plus half at squared to describe this path, or 1.05 equals ut sine 40 and then minus 4.9 t squared. Okay, that's basically an equation for the trajectory of this ball vertically. If I then do the same thing but horizontally, so we want to get to a horizontal displacement of 10 with an initial speed of u cos 40 horizontally, and we know that there's no acceleration horizontally. So I can use s equals ut plus half at squared here, but it's going to be a bit simpler because a is 0. So we're just going to have 10 equals ut cos 40, and that's it. Now I've got two equations here, both of which contain u and t, so I should be able to solve them simultaneously to get a solution for u and t. I think what I'm actually going to do is eliminate t, because I'm just after u here. So this one here I'm going to rearrange to give me t equals 10 over u cos 40. Now I'm going to substitute that in to this one. So my equation is now 1.05 equals u times t, which is 10 over u cos 40 times sine 40, minus 4.9 times t squared. So 10 over u cos 40 all squared. And now I've got an equation just in terms of u to solve. It's not a particularly nice equation, but we can solve it to find u. So this term here, the u's will cancel out. I've got a u divided by u. So they're going to cancel out. The 10 will stay there. I've also got a sine 40 divided by a cos 40. So I'm going to end up with 10 tan 40. You could work this out as a number instead, but for now I'll write it as 10 tan 40. And then we've got minus, well, when we're squaring this fraction, that's going to be 10 squared divided by u squared and cos squared 40. So on top I've got 100 times 4.9, so that would be 490 over u squared cos squared 40. Okay, and that's obviously the same as cos 40 times cos 40. Right, that's a little bit nicer. I'm going to do 1.05 minus 10 tan 40. I'm just going to leave it as a decimal at this point. So 1.05 minus 10 tan 40, that gives me minus 7.341 equals minus 490 over u squared cos squared 40. Then what I'm going to do is divide both sides by minus 490. So I get 0.014982-ish. I'll probably just keep that in my calculator really, is 1 over u squared cos squared 40. Okay. Now what I'm going to do is I'm going to times both sides by cos squared 40. So that's like doing 0.014982 times cos 40 and then times cos 40 again is what I'm actually doing on my calculator. Now I'll leave me with 1 over u squared. So times cos 40 times cos 40. So this gives me 1 over u squared. So now I'm just going to do 1 over both sides. So on my calculator I'll just do 1 divided by answer, which then gives me u squared equals 113.75. And then I can square root it. So I get 10.67 meters per second. That's my final answer. So that's certainly a trickier question. Okay, but it really helps in terms of structuring the problem if we think about this as like a coordinate system. So it's just about, it passes through the point 10, 1.05, where this is the origin. And we can use s equals ut plus half at squared to help us model it. This is always a really good equation to use if we're modeling where something is. Okay. Actually, there's part B here. State 2 factors that can be ignored by modeling the basketball as a particle. So if it's a particle, we're going to assume that it's got no mass, and we're also going to assume that its dimensions are so small that things like air resistance doesn't matter, because a particle is basically just a point rather than an object. So it's very small, so air resistance doesn't really matter. We can also neglect things like spin of the ball and things like that as well. This is also the challenge question from exercise 6C. And I've also made a note here that you could use vectors to lay out your work. So rather than always thinking, oh, here's the horizontal stuff and here's the vertical stuff, we can actually combine them into a vector with the x information at the top and the y information at the bottom. So horizontal stuff and then vertical stuff at the bottom. And this might help us in our working a little bit, just to lay it out a bit neater. So a vertical tower is 85 meters high, and a stone is projected at a speed of 20 meters per second from the top of the tower at an angle of alpha below the horizontal. Okay. So here's my tower. Okay. And we're projecting the first particle, and we're projecting it below the horizontal, so it's coming down at an angle like this. Okay, with a speed of 20. And the angle was alpha below the horizontal. And I was just going to label the height on there. So this is 85 meters. Okay. At the same time, a second stone is projected horizontally, so not really at an angle, just horizontally, at a speed of 12 meters per second from a window 45 meters above the ground. So it's just coming horizontally at a speed 12. That height was 45 meters. Okay. Given that the two stones move freely under gravity in the same vertical plane, so that just means they don't sort of cross over one another, they just follow in exactly the same sort of slice of the diagram, and that they collide in midair, show that the time that elapses between when they are projected and the moment they collide is 2.5 seconds. So my general approach here is I'm going to try and make an equation modelling the displacement of this one and an equation modelling the displacement of this one and set them equal to each other to find where they intersect. I'm going to call this particle A and this particle B. Okay. I'm going to do B first, just because it's a bit simpler because it's horizontal. And we're going to use s equals ut plus half at squared to model its motion. And we're going to do it as a vector. Okay. So at the top of my vector, I'm going to do the horizontal stuff. So horizontally, if I apply this, u is obviously 12, and t is just t. And horizontally, there's no acceleration. So this bit is just 0. So that's done. For the vertical part, well, because it's fired horizontally, its initial vertical speed is actually 0. And then we've got plus half at squared, so that's going to be minus 4.9 t squared. So that's half of minus 9.8, because we're thinking vertically now. But also it starts, if we assume that this point here is the origin in 0, 0, it starts from a height of 45 meters up. So we need to put plus 45 on the end. Because then when t is 0, it starts from displacement 0, 45. So that's the motion of particle B. If we do the same for particle A, so horizontally, its initial speed is 20 cos alpha. So it's going to be 20 cos alpha and then times t. So I'm going to write it as 20t cos alpha. And then vertically, its vertical speed is going downwards at 20 sine alpha. And because it's downwards, it's going to be negative 20 sine alpha. So that'd be negative 20t sine alpha, because it's u times t, and then plus half at squared, so that'd be minus 4.9 t squared. And this one starts from a height of 85 meters, so I just need to add on 85 meters at the start. And there we go. So these two vectors describe the path of these two projectiles. Now to find where they intersect, that's quite easy. I can just set them equal to each other to find where they intersect. So I've got 12t and then minus 4.9 t squared plus 45. That equals 20t cos alpha minus 20t sine alpha. Okay. Now to solve this, we can just treat the top and bottom separately. Okay. So if I just look at the top equations, I've got 12t equals 20t cos alpha. If I divide it all by t, then 12 equals 20 cos alpha. And I could divide by 20, so 12 over 20, that's 3/5. So 3/5 is cos alpha. And I could use that to then find sine alpha. Okay, I could do inverse cos to find it, and find the actual angle, find angle alpha, but it's probably a bit nicer to do one of these triangles like we do when we're doing forces sometimes. So if this is alpha, cos is adjacent over hypotenuse, so that's 3, that's 5. Well, to find this one, I can use Pythagoras, 5 squared minus 3 squared. Square rooted is 4. So using that diagram, I can now see that sine alpha, which is opposite over hypotenuse, is 4/5, which I can use in my next calculations. So let's look at the bottom equations now. So I've got minus 4.9 t squared plus 45 equals minus 20t. Now instead of sine alpha, I can write 4/5 minus 4.9 t squared plus 85. And this is an equation just in terms of t, so I hope I can solve it. First thing I can do is get rid of the minus 4.9 t squared on both sides. So I get 45 equals minus 20t times 4/5 plus 85. And then I can solve that from there really, and I get t equals 2.5 seconds. Okay, so I guess the main difficulty in this question is setting it up right. If you can get to this point here, then it's definitely solvable. And using vectors is a useful skill in mechanics. You don't have to lay it out in vectors. You could lay it out as like all the horizontal stuff and then do all your equations, and all the vertical stuff and do all your equations. But sometimes this is quite nice as a kind of a complete description of what is happening for object B and a complete description of what's happening for object A. Okay. Okay, in this next question, I want to look at how we can actually look at these problems just algebraically. So a projectile is fired at speed u and angle theta from the ground. So we're not doing any platforms here, it's just from the ground. Okay, and it's fired with speed u, angle theta. And we're going to find the three kind of usual things that we can work out: the maximum height, the time of flight, and the range for this particle. So the initial vertical velocity is going to be u sine theta, and the initial horizontal velocity is going to be u cos theta. Okay, just do it in terms of u and theta. Now to find the maximum height, you can say, looking vertically, u is u sine theta. A is going to be negative 9.8, but I'm going to write it as minus g, just to keep it algebraically. V is still 0 at the top, and we want to find the displacement, which I'm going to call h. So we can use v squared equals u squared plus 2as. So we've got 0. Now u squared would be u squared sine squared theta plus 2as, so that's going to be minus 2gh. And if I rearrange this for h, I'll get h equals u squared sine squared theta over 2g. And you could use that as an expression to find the maximum height, provided that it's fired from the ground. Now, I wouldn't advise using that as a formula, but it is useful to think about these things and how we can derive them. Now, the time of flight. So I'm going to use the shortcut. Actually, I'm going to find the time to the top and then double it. Okay, so the time to the top, or the time to the peak, we could call it, u vertically is u sine theta, v is 0, t is what I'm trying to find, and a is minus g. So we can use v equals u plus at. 0 is then u sine theta minus gt. And then I can rearrange this for t. So t is going to be u sine theta over g. You could still get this result from doing it using displacement equals 0. You would end up with the same answer for t. But that way is probably a bit easier here. Oh, actually, I'm going to finish this off here, have we? So we need to times that by 2. And we would then get 2u sine theta over g. Because this was the time to the top. So times it by 2, the time of flight for the whole trip is going to be 2u sine theta over g. Let's just show how to do it the other way as well. Do it in a different colour. So, or we could have said the displacement is 0. Okay, because when it reaches this point down here, the displacement is 0 again. U is u sine theta. A is minus g. And we want to find t. S equals ut plus half at squared. So 0 is going to be ut sine theta minus half gt squared. I could factor out a t. Like that. So either t is 0, which is obviously at the start, or u sine theta minus half gt equals 0. And if you rearrange that, then you will get t equals 2u sine theta over g. So you still get to that same answer if you do it that way. Well, now that we've got the time of flight, we can calculate the range. And for the range, so the horizontal distance, we obviously want to think horizontally. So u, if I look back at my diagram, horizontally is u cos theta. The acceleration horizontally is 0, because gravity only acts vertically and there's no air resistance, so the acceleration horizontally is 0. And we want to find the distance, so I'm going to call it x. And the time of flight for the whole journey is 2u sine theta over g. So I can use s equals ut plus half at squared, which is basically just going to be s equals ut because a is 0. So the range, or x, is going to be ut. So that's u cos theta times 2u sine theta over g. Or we could write that as 2u squared sine theta cos theta over g. And we could use that as a formula for the range if we did want to. Again, I wouldn't recommend remembering it and using it as a formula, but we could do. It's also quite a nice equation because we've got 2 sine theta cos theta in there, which I'd hope you recognise as a double angle formula for sine 2 theta. So I could rewrite this as u squared sine 2 theta over g, which is quite nice. Okay. Here's quite a nice algebraic question. So when a particle is projected from a point with speed u at an angle alpha, moves freely under gravity. So we've just got a simple case where we are projecting it at speed u and angle alpha. Okay, so the initial vertical is going to be u sine alpha, and the initial horizontal is going to be u cos alpha. And we've got to show that if the horizontal distance is x and the vertical distance is y, that this equation is true. Okay. So what we're going to do is we're going to do it horizontally and vertically separately, and then we're going to put them together to make this one equation. This is basically akin to going from a parametric equation, so we're going to describe x in terms of t and describe y in terms of t, and turning it into a Cartesian equation, y in terms of x, like this. Okay. So let's do horizontal first of all. Okay, and we're just going to do displacement, so we're going to use s equals ut plus half at squared. So horizontally, the horizontal distance is called x. So ut would be u cos alpha times t. So it's going to be ut cos alpha. And the acceleration horizontally is 0. So it's just s equals ut. Vertically, the vertical displacement is called y. And it's going to be ut. So it's going to be u sine alpha times t. So that's ut sine alpha. And then plus half at squared. So it's going to be minus half gt squared. Okay. Now these are basically parametric equations for x and y for the displacement of this particle. I've got to try and get them in this form. So I've got to try and eliminate my parameter t. Okay. So I'm going to rearrange this top equation to give me t. So I could write t as x over u cos alpha. And I'm going to substitute that into here. So this equation now becomes y equals u times t, and t was x over u cos alpha times sine alpha, minus half times g times t squared, so times x over u cos alpha squared. Now this is basically the answer, but I've just got to rearrange it and make it look like how they want it. So this first term, the u's will cancel out, and I've also got a sine alpha over cos alpha. So this will just give me x tan alpha. This next term at the end, I've got minus half g, and inside the bracket I've got x squared over u squared cos squared alpha. Okay, so I've just squared everything inside the bracket. Now notice what they wanted at the front. They wanted this gx squared over 2u squared. So that is fine. We've got all those bits in there. We've got the g, and we've got the x squared. They get multiplied. Now I've got a half. That's obviously the same as dividing by 2. And I'm also timesing by a u squared on the bottom. So this is a bit like 1 over u squared. So I've got that bit. And the things that are left over then would be 1 over cos squared alpha, like that. Okay, this term here is exactly equivalent to this one. It's just a different way of writing it. I'm going to leave that bit there, because that was in the question, that was what they wanted. 1 over cos squared, let this do this to the side, 1 over cos squared alpha, that is sec squared alpha. And you might remember an identity from trig, 1 plus tan squared alpha is sec squared alpha. So actually I can replace this bit in the bracket at the end as 1 plus tan squared alpha. And this is then the result that they wanted in the question. So a little bit tricky algebra there, and so you involve some trig identities too, but the projectiles content is actually exactly the same as we've been doing. Okay, it's just more algebraic. Okay, for the second part, I'm just going to put this question a little bit further down. So it says a particle is projected from a point O with speed 28 at an angle alpha. So basically we know that U is 28, but alpha is still going to be alpha. And it passes through point B, which has got a horizontal distance of 32 meters and a height of 8 meters above the plane. So here we've got an equation that we've made in terms of x and y, and we're basically told the horizontal distance is 32, so x is 32, when y, the height, is 8 meters. So we've basically got a coordinate that this curve passes through. So we can substitute this into here and see if we can work out alpha, which is what we've got to do. So I can write 8 equals 32 tan alpha minus, now g is obviously 9.8 times x squared, so times 32 squared over 2 times, now u, speed is 28, so that's 2 times 28 squared times 1 plus tan squared alpha. And if I work out this fraction here as a number, it's surprisingly not that bad of a number. It's minus 6.4 times 1 plus tan squared alpha. So I've now basically got a quadratic in terms of tan alpha. So if I simplify this a little bit, I have 8 equals 32 tan alpha minus 6.4 and minus 6.4 tan squared alpha. And then I could obviously subtract 8 from both sides. So I've got minus 6.4 tan squared alpha plus 32 tan alpha, and then minus 6.4 minus 8, so minus 14.4. So I've got a quadratic. I can then solve that quadratic. I'll just use my calculator to do that. To get tan alpha equals either 4.5 or tan alpha equals 0.5. And then I can do inverse tan of those two to get either 77 degrees or 27 degrees to the nearest degree. Okay, so it's a little bit approximate, but those would be my two options. So there's two different angles I could fire this at to make it go through that point, 32.8. Okay, that's what this kind of answer means. Now to demonstrate this, I've put together these two equations here, the x and y, as parametric equations in Desmos. Okay, so you can see here, this is my x equation, ut cos alpha. I've just used a instead of alpha. And then my y coordinates were ut sine alpha minus half gt squared. And I've set u equals 28, like in part B. Alpha I've just set to 70 degrees for now, so I can change the angle that I fire it at here. And g is just 9.8. Okay, I'm not going to change what gravity is. You can see if I change the firing speed to be lower, it goes much less far. Okay. So what we wanted to find is what angle do I fire it at for it to go through 32.8. So let's put that point on, 32.8. Okay, so I want to fire it through that point. And u has got to still stay as 28. And the two angles we calculated, well, one of them was 77 degrees. So, okay, it's not quite exact because of the rounding on there, but 32.8 is about there. And then if we change the angle to 27 degrees, it also goes through it at that angle too. Okay, it's a bit of a shame it wasn't exactly on the 77 there. I think it's actually 77 and a little bit, isn't it? There we go, something like that, about 77.5. I think it was just less than 0.5, so rounded down to 77. But there you go, so I can change this angle, and I can get it to go through that point. I can get it with that angle, or I can get it with a much shallower angle down here. Okay, so this is a really nice application of parametric equations and Cartesian equations. Okay, so I'd advise you now have a go at probably mixed exercise 6, which is just the end of chapter questions on projectiles, and probably start at number 3, but you can pick and choose which ones you like. I'd also advise maybe having a look at some exam questions. If you look on Physics and Maths Tutor, there's plenty in there on projectiles, especially if you look in the Mechanics 2 section. Okay.